So good morning, everyone. I'd like to start by saying thank you to the organisers for giving me the opportunity to present today. It's always really nice to present at the Phantom Conference, so thank you very much. Today I'm presenting on some work that was published last year. It forms the second paper in a series of 3 papers looking at this particular topic, where we're trying to make observational predictions for these mergers of 2 supermassive black holes. Like, what could we potentially observe to show these mergers? And so let's start by talking about how supermassive black holes actually merge. Supermassive black holes reside at the centers of galaxies, so the first stage of this process is you have to merge 2 galaxies together. Each of these snapshots here is an image of a different galaxy, but showing the stages in this evolution. And so you can see that we start with 2 separate galaxies. They interact, they start to tidally deform, and then by the end of this story, you have one galaxy that presumably has 2 supermassive black holes bouncing around inside of it. And over time, due to dynamical processes and due to scattering effects, these black holes move closer together until they're separated by about 1 parsec. Over time, they then shrink to be even closer until they're about 10 to the negative 3 parsecs away from each other. And at this stage, we actually understand pretty well what's going to happen here. At this stage, the black holes get close enough that they emit gravitational waves, and that promotes them to their final merger and to coalesce into one black hole. But the bit that I glossed over, this bit at 1 parsec and how you go from 1 parsec down to 10 to the negative 3 parsecs, this bit is actually quite difficult for us to explain, to the point where it's called the final parsec problem. And the final parsec problem has a bunch of different solutions proposed for it. Probably in nature, some combination of these things are happening depending on your environment. But the one that we're most interested in for the purposes of today's discussion is this gas accretion here, or this gas-assisted migration. And the idea is fairly simple. You have your supermassive black holes. They're supermassive, so at some point they've definitely accreted material. And most of the time black holes accrete material through an accretion disk. So it's reasonable that at least one of these black holes still has an accretion disk around it or is still potentially actively accreting. We also know that, so most of the people in this room simulate protoplanetary disks, or quite a few people simulate protoplanetary disks, and their interaction with planets. And so we know when you put a planet in a disk that the interaction of that planet with the disk can induce these tidal torques that moves the planet closer to the central star. The same idea is what's happening here. If this secondary black hole is able to interact with the disk, it may be able to migrate closer to the primary black hole and to shrink the distance between them so that they can get down to a distance where they emit gravitational waves and then finally merge. We can characterize the components in this system by their angular momentum vectors. So the first one, the primary black hole, that's the one with the disk, that has a spin angular momentum vector straight up the page here representing the direction of its rotation. The second black hole, by extension, also has a spin angular momentum vector, but the far more important quantity for this particular black hole is its orbital angular momentum vector, so describing its orbit around the primary black hole. You also have the disk, of course, and that has an angular momentum vector. And strictly speaking, that angular momentum is a function of radius. And so it should change, potentially it could change, as you cross from the outer edge of the disk to the inner edge of the disk. Now what you'll notice from the sketch that I've given you is that none of these vectors are aligned with each other. And this is a difficulty with this model, right? When these black holes, in order to get to this stage in this merger story, they've gone through this really chaotic kind of interactions. And so we have no assumption, no reason to assume or justification to assume that these things should all be coplanar. And in fact, we have strong belief that they should all be misaligned with each other. We can represent the misalignment between the most important misalignment between the primary black hole and the secondary black hole by this angle theta. And this angle actually has a very interesting observational prediction from this model. If you have these 2 black holes and you introduce this disk, this viscous component into the system, over very long timescales, irrespective of what misalignment they started with, you expect them to damp down to coplanar, for everything to become aligned on very long timescales. And so if we observe with telescopes, for example, like LISA, that Martina was mentioning yesterday, if we observe like a population of gravitational wave signatures from the mergers of these black holes, we would then expect, if disk-assisted migration is important, that they should all be coplanar mergers, right? And so, in fact, if we can observe that, it will be a very strong signature that disk-assisted migration is helping in the merger of these black holes. So the angle suddenly becomes quite important. We can estimate how that angle changes between these 2 black holes with this expression here, d cos theta dt is equal to the dot product between the rate of change of the the rate of change of the spin vector of the primary black hole and the orbital angular momentum vector of the secondary. Now this first term ultimately comes from this expression here. This is the back reaction of the disk onto the primary black hole. And the important part of this expression is this J cross L. This is the cross product of the green vector and the black vector, and it's summed across the entire disk. But the angular momentum vector of the disk presumably is allowed to change as a function of radius, and so the shape of the disk ultimately is what's determining this d cos theta dt. The shape of the disk is going to influence and impact on that observational prediction we make for what angles these black holes should have over time. And the shape of the disk is actually a really difficult thing in this problem, right? Because you have these competing effects from the two black holes. The primary black hole is rotating, it's exerting a lens-tearing torque on the disk, and in combination with viscosity, that lens-tearing torque acts as if to pull the inner edge of the disk into alignment. In other words, it's trying to snap the inner edge of the disk to be in the same alignment as the black hole spin. By the same token, the secondary black hole, that one that's orbiting the primary, that exerts a tidal torque on the disk. And the effect of that is to try and pull the outer disk into alignment with its orbit. So you have these competing effects in the disk. The inner edge is getting pulled towards the primary black hole, and the outer edge is getting pulled towards the orbit of the secondary black hole. And I've just motivated to you that these two things should not be aligned. They should, in fact, be misaligned. So the presumption is that the disk takes on this kind of warped profile. And so the presumption is then this angular momentum vector of the disk, which can change as a function of radius, almost certainly is changing as a function of radius, and you have this kind of a curved shape between the inner edge of the disk snapping to the primary black hole and the outer edge snapping to the secondary black hole. Okay, and so the two research questions that we have in this problem, the first one is, what shape does the disk take? In a general kind of a picture, depending on, like, irrespective of where these black holes start and their initial misalignments, what shape does the disk actually take? And the second research question is, how does this affect the alignment of these black holes? And that's because the shape of the disk here impacts on how we calculate d cos theta dt, and that's our observational prediction. Over long time scales, what alignment do these black holes have? So, to tackle this problem, David Gerosa in 2020 and collaborators wrote down some complex looking equations, but really we've got two equations. The top one here is representing the evolution of the surface density profile of the disk. So this tells us where the mass is in the disk as a function of time. And their second equation here is telling us the evolution of the angular momentum vector, so the shape of the disk over time. The important thing here is that they include these two different terms, one representing the primary black hole trying to pull the inner edge of the disk to alignment, and the second one representing the effect of that secondary black hole trying to pull the outer edge of the disk into alignment with its orbit. And in doing this derivation, Gerosa et al. Used these two particular length scales. The first one is this RLT. It's a characteristic length scale related to the lens-tearing torque, and conceptually it's the distance from the primary black hole where that lens-tearing torque, the rotation of the black hole, has the strongest effect on the curvature or the shape of the disk. The second length scale they used was this TID, tidal. It's the tidal radius, and it's the same idea. It's the length scale at which the tidal torque from the secondary black hole is able to change the shape of the disk the most. Now, these two length scales have been previously defined. That's not new. The thing that is new is that Gerosa et al. Took the ratio of these and introduced this new kappa parameter. They parameterized all their results by this kappa number, and so it's important for us to understand in the discussion that we're going to have. We can rewrite kappa in terms of the physical properties of the system. So kappa depends on the mass of the primary black hole, the spin of the primary black hole, the mass of the secondary, the separation between these two black holes, the aspect ratio of the disk viscosity, and this zeta term here, this is also just a function of the disk viscosity. So these last two terms are just disk viscosity terms. And conceptually, what kappa tells us is the importance of the secondary black hole on the evolution of the disk. So a very high kappa value, which you might get by, for example, having a very massive secondary companion, a massive secondary black hole. That means that a very high kappa value means that the secondary is driving the evolution of the disk. That's the main player in the game. If instead kappa is a really low value, that tells you that the secondary is not contributing very much. The primary black hole is really what's driving the evolution of the disk, and that could be achieved, for example, by having a very large separation between the two black holes. And in the limit, the kappa tends towards 0, that's like the secondary doesn't even exist. We can pretend it doesn't exist. Okay. The most important thing, however, to understand about kappa is that it's a non-dimensional number. Like a Stokes number or like a Reynolds number, it's a non-dimensional number. And when it comes to designing our 3D calculations, this gives us a huge advantage for how we actually choose the parameters in our simulations. Okay, so back to Gerosa et al. And their semi-analytic model. They go through a series of steps in order to solve this problem to create this prediction for what the inclination between these two black holes should be on long time scales. The first thing they do is they choose a bunch of parameters, so the masses, the separation of the black holes, those kinds of things, and they calculate their kappa value. For this example I'm showing you, kappa is 0.1, which tells us the secondary is of moderate importance in determining the evolution of the disk. They then, for a given angle, initial angle between the black holes, then solve for the evolution of the surface density profile and the angular momentum profile as a function of time. And so you can see here from these angles that they start with here, across time, the black holes tend towards alignment. And this is kind of what we're expecting, right? We add this viscous disk to this process, and over time, we expect everything to go down to coplanar. But the angles that we start with should be truly random. So they also consider retrograde inclinations as well. And so these are the warm lines at the top here. And you can see from the model that these black holes here are tending towards prograde coplanar alignment over long time scales as well. Perhaps the most important result, however, from Gerosa et al. 2020 was not the results that you see here. The most important result was when they didn't find any results at all. In certain parts of the parameter space, Gerosa et al. Found that, in fact, the semi-analytic model just broke down. It stopped working. Practically speaking, the integrator stopped integrating. And this presented a massive problem because you can see here for these counteraligned disks, we want to know what's happening as they continue, but they hit this region where we can't solve anymore. And we can't start any disks in this region either to see what's happening there. Now, Gerosa et al. Repeated this kind of exercise for a range of different kappa values, shown across the x-axis here, for a range of initial inclinations, and then color-coded for a range of disk viscosities. And they found, in this graph here, the shaded region is where their semi-analytic model breaks down. They found, for a huge region of their parameter space, that their semi-analytic model could not produce results. And this suddenly became very, very interesting, right? And if it just so happens that you did your PhD on breaking black hole disks, you might have a really strong gut feeling for what's happening in this region here. But if these guys are your collaborators, you'll also be told very firmly that you have to prove it with simulations back. So this is what we did. Myself and Enrico Ragusa, we decided that we would try to tackle this problem with 3D simulations using Phantom. And our idea was this. For where the semi-analytic model works in this region out here, we want to confirm their results. We want to confirm this transition between where their model works and then where it stops working, and then use our 3D calculations to understand what's happening inside that region where the semi-analytic model stops working. In other words, we want to pepper this parameter space with as many of these things as we can using Phantom. In order to do that, we ran a suite of 143 simulations. You can see we've got a bunch of different things that we tested and varied in our calculations. Common to all of our simulations, though, we used a fixed potential with a post-Newtonian approximation. Now, Mega yesterday was talking about how her prediction from the post-Newtonian model for how close her star should be, her tidal disruption event should be, was off by about 6% when compared to the full GR approximation. We avoid that kind of difference by making sure that the inner edge of our disk is slightly larger so that it's at a region where the post-Newtonian approximation is a very good approximation to the GR terms. In order to respect the fact that we're using a fixed potential, we set the mass of the secondary to be much lower than the mass of the primary. And we're allowed to do this because we are parameterizing everything by this kappa value, and it's a non-dimensional number. So what that means is as long as we get to the number, it doesn't really matter what choices we made to get there, we expect to see the same physical behavior. Okay, and so from our suite of simulations, we found, broadly speaking, 3 distinct behaviors that occur. I'm going to show you some movies to explain these. In all of the movies, you've got a face-on view on the left panel and a side-on view on the right panel. The blue dot here is representing the secondary black hole, and the primary black hole is at the center here. It's invisible because it's a fixed potential, but it's tilted like in this direction here. The angular momentum vector tilts back and forth this way, depending on how we set it at the beginning of the simulation. Now, the first thing you'll notice as our simulation runs is that we develop these really lovely strong spiral arms. That's very interesting. It's not predicted by the 1D model because they assume axisymmetry in their model. The other thing you can see when we look particularly at the right-hand side here for this particular simulation is that the disk changes orientation. And if you look really closely, it does warp a little bit as well. We have some curvature in the disk. So this is the first kind of behavior we find, warping. The second kind of behavior that we find is disk breaking. So here we have these two external torques affecting the disk, and the disk is fragile enough that when exposed to these torques, it breaks into these rings of precessing material. Sometimes we find rings, like one ring in the simulation, sometimes we find multiple rings, and each of these rings is allowed to precess with this local precession frequency, which around a rotating black hole is strongly a function of radius. And so we see that these things precess at very different rates, and so you get this kind of hot mess in the middle of these rings moving about. The third kind of behavior that we find is, to our knowledge, new behavior. Only a handful of the simulations in our suite show this, where we find unsuccessful breaking. So in these calculations, the disk looks like it's trying to break. It's really trying to break, particularly in this right-hand panel you can see. You've got this ring, it looks like it's trying to separate, but it never actually makes it, right? It never actually truly comes off. And so we refer to these disks as unsuccessful breaking. We can categorize all of our simulations, all 143 simulations in our suite, into these categories. We have warping on the left-hand side, unsuccessful breaking, and then we have two different kinds of breaking. Sometimes you get multiple rings, which is the movie I showed you, and sometimes you get just one ring breaking off. And so we separate those two in our analysis. We can understand the difference between these categories by examining the surface density profile as a function of radius and the warp profile as a function of radius. And the warp is a parameter defined by this expression here. Conceptually, it's like how steep is the disk changing, basically. Is it like curving really, really quickly or curving slowly? And so for a disk that experiences warping, the surface density profile is quite boring, the evolution here, and we see negligible evolution in the warp profile. For a disk with breaking, whether it be a single ring or multiple rings, in the surface density profile we see a true minimum where the disk is broken, and then in the warp profile we see a maximum here. And we know from previous work led by Suzanne Doan that when you look at the warp profile, if you have this local maximum and it steepens over time, that's definitely disk breaking. It's irrefutable evidence of disk breaking right there. In this kind of in-between case where we have unsuccessful breaking, we see a steepening in the warp profile, but the minimum that we have in the surface density profile, it never dips down to a true minimum. It's always just like a little local minimum. And that's how we differentiate the unsuccessful breaking with the true breaks. So we wrote a little script that looks at each of our calculations, looks at the surface density profile and the warp profile, and determines which category our simulation fits into. So here's our comparison with the semi-analytic model from Gerosa et al. This is, across the page here is kappa. This is the parameter space they're examining, with the right-hand side being that the secondary is more important in the evolution of the disk than the primary. Up the page, we have the relative inclinations we start with between these black holes. And then in the shaded regions here, this is where their semi-analytic model breaks down. They can't predict what's happening there. We've color-coded by the different disk viscosities, and then these symbols here are representing the different kinds of results that we have based on those movies that I just showed you. There's a lot of dots here. There's not quite 143 on this plot, but there are a lot of dots. So let's have a look as an example at these blue ones here. If we start with the low inclination and then go higher, our lowest inclination simulation here, we have a square which represents no breaking. And that's in the region where Gerosa et al.'s model predicts we should find disk warping. So outside of this line of criticality, where their model predicts warping, we recover warping in our 3D calculations. When we get to this region here where their model breaks down that line, we find that the disk here shows unsuccessful breaking. It's trying to break, it doesn't quite make it. And inside this region where their model can't predict anything, we find that the disk breaks. In this particular case, these disks all break into multiple rings. You keep going up till we get to the retrograde simulations, and then when we get back to that region of criticality, we find that the disk stops breaking, and as soon as we're back in the region where their model can predict solutions, we find disk warping again. And that kind of qualitative result is true for most of the simulations that we run. So in other words, when we compare to Davide Gerosa's model from 2020, in the region where their model is valid, we find disk warping. In the region where their model is unable to produce results, we find disk breaking. So in other words, we've shown that their model breaks down the moment that the disk begins to break. We do have some discrepancies. I don't have time to discuss them right now, but we cover them in the paper, and I'm more than happy to chat to you about them at another moment. Perhaps one of the most interesting things that we found from this suite of simulations is if we looked at some of these really carefully, we found some kind of extra things happening. And one of these is that normally when we talk about disk breaking and we try to assess whether a disk is going to break or not, we use the global disk properties like the aspect ratio of the disk and the viscosity of the disk. And for the first time in our simulations, we found a local feature that can determine whether the disk breaks or not. So here to demonstrate this, I've got a comparison between two simulations. I've got the surface density profile at the top here and the warp profile at the bottom here. And the solid lines are an earlier time step, and the dotted lines are a later time step. And I want to start by focusing on the purple lines to begin with. So in the purple simulation here, we have very strong spirals driven by that interaction with the secondary black hole. And you can see these spiral arms at this peak, this little hill here in the surface density profile. As the warp profile propagates from the inner edge of the disk to the outer edge of the disk in the purple lines, the moment it's increasing before it hits the spiral arms, but the moment it becomes coincident with the spiral arms, the warp profile begins to decrease. In other words, the disk was going to break, it was on its way to breaking, it hit the spiral arms, and it stopped breaking. Right? If instead we have weak spiral arms, shown by the green line, these spiral arms are of much smaller magnitude. You can see in the surface density profile, when that warp propagates outwards, in the green line here, you can see that the warp continues to increase. And in our density rendering, you can see actually that the disk does begin to break. So in other words, we found that if you have this warp, it's going towards the spiral arms. If you've got just the right combination of parameters, it's possible for the spiral arms to stop the warp and to actually prevent the disk from breaking. And to our knowledge, this is the first time that a local feature can dictate whether the disk breaks or not. Okay, but let's go back to our research questions. The first one was, what shape does the disk take? Well, I can tell you from our calculations, the disk can be warped, it can be unsuccessful breaking, or it can be two different kinds of breaking with maybe one ring or sometimes maybe even multiple rings going around. How does this then affect the evolution of the angle between these black holes? Well, from our calculations, our simulations run for a really, really short time period. This is a limitation of the calculations that we're running. We can't actually model the entire merger or anything like that. But what we can do is we can measure the back reaction from the disk onto the black hole, what it would be, and then estimate what d cos theta dt is, and infer what might happen on long time scales. So this is what we do. Here, as a function of time across our simulations, I'm showing d cos theta dt on this axis here, and I want you to start by having a look at the dotted lines on this plot. The dotted lines are representing simulations where the disk warps but does not break. And you can see that d cos theta dt tends to some kind of a constant over time. If you instead look at the solid lines, these are simulations where the disk breaks into one ring. So you have two different sections of the disk, and the inner part is processing much faster than the outer part. And here you can see that d cos theta dt now takes on this oscillatory kind of behavior. If we then extend this to have a look at the disks that have multiple rings breaking off, what we see is the same kind of pattern, but far more complicated. We see oscillations and sometimes very complicated kind of summations of oscillations occurring here. And we can understand this in terms of kind of just geometry, which at the end of the day can be a little bit boring. But we have on the top left-hand corner as our reference, this is the equation that we're solving. And we're going to be talking about how the angular momentum vector changes as a function of radius, depending on the shape of the disk, and then how that then affects that d cos theta dt that we're interested in. Here's our disk here. We've got the spin angular momentum of the primary, and then we've got the angular momentum of the disk, which at the start I told you can vary as a function of radius, but I just drew it simply with just one vector. If instead I represent this system with a set of concentric rings, each of which has its own angular momentum, we can consider this summation across the disk just in terms of the summation essentially of the cross product of these things, right? So this J cross L summed over the disk can be expressed by the cross product of the green vector with each of those grey vectors in turn summed together. Now, if each of those vectors is in the same direction, that summation is going to be additive, right? Each time you do it for the inner disk, then the inner ring, the middle ring, and the outer ring, each time you do it, it's going to add to your summation, yeah? And so that's our first kind of scenario where we have warping in the disk and we have a positive d cos theta dt. If instead, part of your disk has broken off, and part of your disk has processed around faster than the rest of it, it is possible for you to have a region of the disk which has opposing angular momenta. If we then do this summation, the outer two rings here are going to sum in the same direction that we had before, but the summation term that comes from this inner ring is now going to be in the opposite direction. And so the sum that you get, the total sum you get here is going to be smaller than what you started with, right? And how that summation changes is going to depend on the orientation of that inner ring. Over time, it's going to go through regions where it's going to be aligned with the outer disk, and so you get a maximum summation. And sometimes it's going to be misaligned or counteraligned with the outer disk, and so you get the smaller summation. And then it's going to go back to being fully aligned, and you get a larger value, and then back to counteraligned, and you get a smaller value. And so you can see that we might get these oscillations in the profile that we're measuring as a function of time. And the oscillations that I showed you before, we can show occur on the time scale that inner ring is actually processing in our 3D simulations. By extension then, we then can say that, well, if you have this scenario where you have multiple rings processing in your simulation and they all have different orientations, you're going to get this effect happening but by multiple rings at the same time. And so you get this summation occurring, but they're all processing on different frequencies at different rates. And so as a result, you're just going to get this really hot kind of mess of oscillations all summed together. Okay. So to summarize, the work that we're doing here is trying to look at the observational signatures that we might find. Sorry, I completely missed something. Let's go back. Sorry, everybody. Right? The important thing here that we say then is this, right? Okay. Sorry, everybody. When you're thinking about d cos theta dt on really long time scales, from this top case here, we would then still expect to see alignment on very long time scales, right? And that's our observational prediction. But if in your disk, you have regions which are processing, differentially processing, and allowed to develop misaligned angular momenta. That means your summation is going to change, and so your ability to align the black holes becomes weaker, right? The more misaligned material you have, the more processing material you have, the slower this alignment should occur. And we could actually create a system, if we wanted to, where you could cancel out the angular momentum entirely, this summation entirely, and so you would have no alignment between these black holes. And so the shape of the disk, what impact does it have on our alignment of these two black holes? As soon as you have disk breaking or disk tearing, they should align more slowly, and sometimes they might not even align at all. Sorry, everybody, for missing that very important conclusion. Okay, so to summarize our work, we were looking at this semi-analytic model and how we can validate the semi-analytic model with our 3D calculations using Phantom. We found in the region where the semi-analytic model works that we confirm their results, and we confirm the region where we switch from the semi-analytic model working to not working. We confirm that line over there. We also can show that in the region where the semi-analytic model breaks down, that's where we experience disk breaking, and we can explain how that can then break down the model. The semi-analytic model, sorry. We also had some exceptions that I didn't get a chance to explain about for very disks with large aspect ratios and large alpha and very large kappa, where we find differences and identify differences in our comparison, and thus we can identify limitations in the 1D semi-analytic model. We showed that a local feature like spiral arms is capable of preventing a disk from breaking, even if you thought it was going to. And we showed that disk breaking hinders, and in some cases prevents, alignment between these two supermassive black holes, which then affects that observational prediction that we're going to make. This work was followed up by Nealon and Gerosa in 2023. This is paper 3 of the series. And these guys showed that based on our results, they showed that there should be distinct populations that we see when we take these gravitational wave observations, which could show us whether or not disk breaking has played an important role in the evolution of this disk-assisted migration for these merging supermassive black holes. And with that, thank you very much. I'm finished.
Very nice talk. I have two questions. Actually, one is, if I understood correctly, at some point you said that some of your numerical results Actually, I mean, the majority could actually explain that where the Gerosa model was failing was because there was the production of new disks. But in some cases, there were some exceptions. So can you elaborate a bit more?
I sure can, absolutely. Just give me a second, because I've got slides. Okay, here. So here I've highlighted two different examples where we have exceptions to our comparison with between the 3D simulations and the 1D semi-analytic model. These ones on the left-hand side, these squares that you can see here, these represent our simulations with the biggest aspect ratio in our parameter suite. We had an H/R of 0.08. And whenever we simulated these disks with this very large aspect ratio, we found that the disks never broke. This square is representing the disk is not breaking. It didn't matter what inclination we used or the 2 kappa values that we used, there was no evidence of disk breaking. And we were able to rule out things like numerical resolution, we were able to rule out potentially like wave-like versus diffusive behavior, all those kinds of things. And our conclusion was that the semi-analytic model, like most analytic models of disks, assumes that the disk is infinitesimally thin. It's like a razor-thin disk, right? And so at some point, that assumption breaks down. And we found that for the parameters that we chose in our calculations, having the aspect ratio of 0.08, so a thicker disk, that's where that assumption broke down. And so we couldn't compare very well to their model there. In addition to that, we also have these purple ones here. The purple ones are representing where we had very high viscosity. And so with very high viscosity, we would expect actually the semi-analytic model to work very well with high viscosity. I'm just going to try and, hold on, show you the actual graphs. Here you can see this, right? These are the disks with very high viscosity. And when we look at the surface density profile, for example, here, the green line is a comparative simulation with very low viscosity. And in this simulation, you've got this peak here, and then the trough here, and then it goes to the outer disk. This is a ring of processing materials. So this green simulation at low viscosity is showing a processing ring that has broken off. And the purple line here is representing that high viscosity case. And our interpretation here is this. With the very high viscosity, you're accreting lots of material. And so where you should have a lot of material in order to break off a ring, you've actually already accreted most of that away. And so as a result, you can't break off a disk anymore. And so that kind of evolution is not necessarily captured by the 1D semi-analytic model the way that we recover it in Phantom. And so we do have some exceptions, but we can explain them in this kind of a sense, yeah. Does that answer your question?
Yeah. And then since you said that they are trying to predict gravitational waves from the system, so I was wondering, what information actually we can recover from the gravitational waves from these systems? Like, for instance, the number of disk forming?
Yeah.
Or not? I mean, I don't know what they found.
This is not my expertise. I have to caveat my answer with this, but my understanding was that they were looking at signatures for the spin and the misalignment. Okay. Is that possible?
Yeah, that's for sure. Yeah.
Sure.
I'm just wondering if you can understand that in how many disks the disk is actually breaking or not from gravitational signal. I was just curious because.
Yeah. So, I mean, my understanding is what they were looking for was that if you observe a population of these things, right, you assume that when they get down to that, like, roughly 1 parsec business, that they all start randomly oriented. And so if there was no disk-assisted migration, when you then observe a population of gravitational waves, you should essentially observe just a random set of orientations, if that's what you can get out of the observations. But if instead disk-assisted migration is the thing that's happening, and there's no disk breaking, for example, let's say everything aligns to coplanar, you then expect in your population to observe essentially almost all of them being coplanar mergers. And so if disk-assisted migration is acting, right? But we've shown that if you have disk breaking, that won't necessarily be true. And in Nathan Seinel's paper, he has these plots where he shows the evolution of the spin between, of the angle between the black holes as a function of time. And he shows across the plane of the sky, essentially, where they all end up. And he shows that they end up in certain regions, depending on where they start and depending on whether disk breaking is important or not. Yeah.
Okay, thank you.
Thanks.
I like very nice talk. I had a curiosity. I mean, I was thinking that of an analogy with like supermassive disks, because here they're saying that spirals like introduce viscosity, so like the disk doesn't break anymore. But so if you would have like a very massive disk, you would have like probably, I mean, you can model it with also cooling. So cooling decrease you have like a self-regulation of the temperature of the disk, and this means that the disk can break maybe. So I was thinking maybe I mean, if this can be like an observable through which you can also find an estimate for the disk mass or not, or if it's too like there are too many things that can.
I think probably there's a lot of things that come into play there. But maybe it is something, a way that you could estimate the disk mass. Disk breaking in protoplanetary disks, I mean, in this scenario, you've got these black holes acting, and so you make some assumptions. Well, sometimes you make some assumptions about the angular momentum balance. But in protoplanetary disks, the angular momentum balance is quite different, and so the mass of the disk does come into whether the disk breaks or not, in a kind of a separate line of argument. And so we should discuss, yes, yeah, with Sal.
Does anyone else have another question?
Yeah, great talk. So I just want to understand the plot in this background. So in these semi-analytic models, am I correct that... Yeah,
do you want me to go back, sorry?
Yeah, well, just...
sorry, this one here?
Yeah.
Yeah.
So am I correct that these lines are roughly where the angular momentum transport timescale in the disk equals the precession timescale of the disk?
It's roughly where the disk begins to break, and that's one of the ways that we can estimate whether the disk breaks or not with the global timescale. Exactly. Whether the disk can communicate the precession faster than the precession occurs is one of the criteria we have to decide if the disk is breaking or not. And so yes, it does correspond to that. In some sense, it does correspond to that. In the semi-analytic model, they were using Gordon-Ogilvy's descriptions for viscosity, and so practically what happened when they're solving this and they get to one of these regions, that part of the routine is unable to continue solving because the surface density profile goes to 0 somewhere, and so how do you evolve viscosity over a surface density profile of 0? It's just not really equipped to handle that kind of a description. And so that's what's happening there. But it is physically, it's conceptually very similar to exactly that. Yes. Yeah.
My understanding was like if I try to warp a disk, if you just simply move it, the total angular momentum of the disk just changes, so you can't really conserve it. So you need to redistribute the angular momentum, otherwise you don't conserve the quantities you need to conserve.
Yeah. So the initial conditions in our simulations are contrived, right? They're the simple ones that we make to start with. And so the total, everything is on long scales, it's moving or processing around the total angular momentum vector anyway. And so the thing to think about is in what we've presented, where the total angular momentum vector starts from, and then as a result, how everything redistributes according to that. But yeah, you're right, yeah.
Okay, let's all go back.
Thank you.